Hi, in this video lab report, I'll be presenting the amount of excess charge on an ordinary object, and this is the physics behind it. The purpose of this lab was to determine how much excess electric tape is on a piece of charged Scotch tape, a common everyday object. Ordinary materials can pick up excess charge through contact or separation, a process called charge transfer, but how much charge? In principle, it's somewhere between 1 electron and roughly 10 to the 5th coulombs, an enormous range. By doing a simple floating tape experiment and building two computational models in GlowScript, we narrowed that down to a specific estimate, approximately 7.07 times 10 to the negative 6th coulombs per tape, and I'll show how exactly we got there. There are three core physics ideas at play here. Electric charge. Matter can carry excess positive or negative charge. Like charges repel, opposite charges attract. Charge is conserved. It's transferred, not created. Second is Coulomb's law, which gives the electric force between 2-point charges. F equals 1 over 4 pi epsilon naught times Q1 times Q2 divided by R squared. The constant 1 over 4 pi epsilon naught equals 9 times 10 to the ninth in SI units. Third is force equilibrium. When tape B floats motionlessly above tape A, its momentum isn't changing, so the net vertical force must be zero. That means the upward electric force exactly equals the downward gravitational force. This gives us the equation we need to solve for Q. We also made two key simplifying assumptions. Both tapes carry equal charge, since they were peeled from the same base tape, and that each tape's charge can be treated as a single point at its center. So here's what we actually observed. In section 6.1, when we brought two U-tapes near each other, we expected repulsion, since both tapes should carry the same sign of charge. In practice, the tape showed minimal noticeable deflection, which could be due to a partial discharge or humidity. When brought near a neutral object, nothing happened, as expected. In section 6.2, we determined the sign of the charge. A plastic pen rubbed through hair becomes negatively charged. When we brought that pen near a U-tape, the tape was attracted to it, which tells us the U-tape was positively charged. This makes sense. When the U-tape was peeled off the base tape, electrons transferred to the base tape, leaving the U-tape with a net positive charge. Now for the quantitative experiment in 7.1. Our system is tape B, the floating tape. The surroundings are tape A below and the Earth. Since tape B's momentum isn't changing, the net Y force is 0. Electric force up equals gravitational force down. And here are the measured values. Tape length is equal to 20 centimeters. The mass of the tape is 1 gram per meter, so mass equals 0.0002 kilograms. Separation when tape B just begins to float was measured at 2 centimeters. The gravitational force is 0.002 times 9.81 equals approximately 0.002 newtons. And since we're at equilibrium, the electric force also equals 0.002 newtons. With those measurements, we can solve for Q. Step 1 was to say the gravitational force equals 0.002 newtons. Step 2 is to set the electric force equal to gravity using Coulomb's law. F equals 1 over 4 pi epsilon naught times Q squared over D squared. Solving for Q squared, we get Q squared equals F times D squared divided by the Coulomb constant. Step 3 is to plug in. Q squared equals 0.002 times 0.002 squared divided by 9 times 10 to the ninth. That gives Q squared equals 4 times 10 to the negative 17th, so Q equals approximately 7.07 times 10 to the negative 6 coulombs. Step 4 is to convert to the number of electrons. Divide Q by the elementary charge, 1.6 times 10 to the negative 19th. That gives approximately 4.4 times 10 to the 13th excess electrons on each tape. In section 7.2.1, we asked what fraction of surface atoms contributed to electrons. Since the tape is essentially one-dimensional, we estimate the number of surface atoms as the tape length divided by the atom length scale. 0.2 meters divided by 10 to the negative 10th meters equals 2 times 10 to the ninth atoms. Our ratio of excess electrons to atoms is 4.4 times 10 to the 13th divided by 2 times 10 to the ninth, which is approximately 2 times 10 to the 4th, meaning roughly 20,000 excess electrons per surface atom. This seems high, which reflects the rough nature of our approximations, treating the tape as purely one-dimensional when it is in fact 3D. Our first GlowScript model represents each tape as a single point charge as its center, directly matching our simplifying assumptions from the experiment. We set M and Q as variables, placed the 2-point charges separated by the measured distance, computed the Coulomb force, and compared it to the gravitational force. With Q set to our experimentally derived value of 7.07 times 10 to the negative 6 coulombs, the electric force matched the gravitational force, confirming our calculation. Our second model used the line of charges starter code. Instead of 1 point charge per tape, we use n equals 10 charges evenly spaced over the 0.2 meter tape length. The total charge Q is divided equally. A small charge is Q over n. For each charge on the top tape, we computed the electric field contribution for every charge on the bottom tape using our E field function. This is superposition. Summing all pair interactions gives us the net electric force on the top tape. We then turned Q up until this force balanced gravity. The point charge model gave Q approximately 7.07 times 10 to the negative 6 coulombs. The line charge model gives us a somewhat different value. In the point charge model, all of Q is concentrated at one spot. In the line model, charges are spread along the 20 centimeters. The line charge model is more realistic since real tape does spread along its length. It better captures how the geometry of charge distribution affects electric force. Two final questions. What if electrons were positive and protons were negative? The physics would be identical. Coulomb's law only depends on the changes in magnitude and sign relationships of charges. Sources of error include the point charge approximation, measuring D precisely, humidity affecting charge retention, handling the tape, and the assumed mass per unit length of 1 gram per meter. We determined that its charge piece of Scotch tape carries approximately 7.07 times 10 to the negative 6 coulombs of excess charge.